Hi guys, now we'll proceed with this lesson, which is on the intermediate value theorem for continuous function, or I will call my intermediate value theorem as IVT. Okay, or another one is also related to what we call as IVP, or you can say this as intermediate okay, value property. Okay, so basically the idea is that, okay, for a continuous function f, okay, this function f is said to have IVP, or the intermediate value property, okay, whenever, okay, it takes two value. If you consider this kind of curve y equals to fx here, okay, this one, and it takes two value at the end of domain x, okay, it also take all the values in between, okay, and between this domain between a and b. So that's mean, for instance, it can also take the value, okay, at the point x equals to c, and the value is y naught based on this curve, or this is y naught equals to fc. Okay, that is just to summarize what is the intermediate value theorem, whereby basically I repeat, if we got like some sort of continuous function and it takes two values at the end of its domain a and b, it also take all the values in between, intermediate value, that's mean the value in the middle, okay, or more rigorously, it is given by the statement of theorem 11, which is called the intermediate value theorem, which says that if f is a continuous function on a closed interval ab, should be a closed interval because we are considering inclusive our at the end of our x domain, and if y naught is any value between fa and fb, so that's mean this is the point a. Okay, so we got our FA, and this is the point B, and we got our FB. So our Y naught is just in between FA and FB. Okay, then this theorem says that, okay, Y naught is also equals to FC, whereby the point C is in between A and B. Okay, in the domain X for some C in the interval closed interval AB. So it will take the intermediate values between the point AV. That is what the intermediate value theorem says. Okay, now, okay, let's consider the following example, which is basically we got our piecewise defined function, okay, 2x minus 2, which is represented by this graph, and then we got a constant function 3, which is represented by this line whenever x is in between 2 and 4. Okay, and we ask why the intermediate value theorem, or the intermediate value property IVP, fails in this case. Okay, first, in order for the intermediate value properties to occur or something in a particular function, we need some sort of a continuous function over finite closed interval. Okay, and to answer the question why, okay, do you think this graph is a continuous function, or it's not a continuous function? Okay, the answer is not a continuous function, because there is a sudden jump from the point 2 here to 3, which indicates that it's a not continuous function over finite closed interval, maybe in this case 1, 4 or something. Is not a continuous function, and in this case the IVT, intermediate value theorem or intermediate value property, fails here. Okay, because of the graph in figure 2.44 that we considered. Okay, the function f is discontinuous. Okay, discontinuous, at x equals to 2, you can see here at x equals to 2 there is a sudden jump here over here, which means that the IVT, intermediate value theorem, conclusion may fail, okay, whereby this is also because it will miss all the values between 2 to 3. Okay, do not cover by some sort of a smooth continuous line over there. There is a sudden jump again, I repeat. Okay, now, okay, one of the important application for intermediate value theorem, okay, one of the application is to find the root, or it is used for root finding, okay, to know that the root exists and we want to get some sort of interval where it exists. That is the application of intermediate value theorem. Okay, for instance, consider example 10, which asks us to show that there is a root, okay, there is a root of x cubed minus x minus 1 equals to 0 between 1 and 2. Okay, it already gives us the answer that the root should lies between 1 and 2. If you consider this graph, okay, according to scale, this is 1 and this is 2, and then this is the curve where we got maybe y equals to x cubed minus x minus 1 or something. Okay, and you can see that this curve intersect the x-axis at this particular point, okay, between 1 and 2, and we want to make some sort of reasoning based on intermediate value theorem that there is a root, okay, and it exists between the interval 1 and 2. Okay, first, okay, we will show this statement by letting, okay, we let fx equals to x cubed minus x minus 1. Okay, we call this part of our equation as fx, of course. Okay, and we will consider fx equals to 0 later. Okay, now we know that, okay, we are interested in this domain x between 1 and 2. Okay, so the boundary is always between what we call as 1 and also 2 over here. That is the boundary. So we will evaluate the boundary. At the boundary, our function f1, okay, we equals to 1 cubed minus 1 minus 1, which is just equals to negative 1, which is always less than 0. And if we check at the right boundary 2, f2, okay, we got 2 cubed minus, okay, minus 2 minus 1, which is 5, which is a positive number or larger than 0. Okay, so from here we know that, okay, from here we know that we got in the first place, okay, the function changed its value from negative in this part of the graph to positive value, okay, and this part of the graph, okay, negative value to positive value. It will cross x-axis, or it will cross, okay, x-axis, sorry, it will cross x-axis at, sorry, okay, it will cross x-axis at this location, okay, and then we know that, okay, at this location we know that our y naught, we call it as y naught because it's x-axis, y equals to 0, or we call it as y naught to be compatible with our IVT theorem. Y naught equals to 0 is in between f1, which is our negative number, and f2. Okay, since, okay, next statement is that since f is continuous, okay, based on IVT, this implies that, okay, there exists a 0, okay, I repeat, there exists a0. Okay, there exists a0. Okay, of f between 1 and 2. Okay, and this is the conclusion based on intermediate value theorem, and we show that based on intermediate value theorem, okay, there exists a0 between 1 and 2, and that's conclude our example 10. Okay, and graphically you can see that, okay, the roots here exist and it lies between 1 and 2, and the root here is basically, if you enlarge this one, it will basically equals to x equals to 1.32, which is of course in between 1 and 2. Okay, with that I think conclude our lesson on intermediate